for QLogic. So his timing is awesome. You can change the next slide. So I'm going to walk you through a little bit about an introduction to QLogic, a little bit of our architecture, but the primary focus of this is we've made a major contribution to OFED, of some technology that you might be interested in, and its impact in OFED itself. Okay, next slide. So, full disclosure. First of all, QLogic is the other InfiniBand company. All right, next slide, or next. We cooperate with Mellanox, and first of all, I'd really like to thank Mellanox. This is an awesome event, and it's an awesome value to the industry. And Mellanox has done a superior job at helping to build InfiniBand over the last 10 years. But we do compete. So, you know, from that standpoint, we're friendly competitors most of the time. Some of the time, maybe not, but most of the time we are. We do have a different architecture for InfiniBand. It's all based on standards. It all follows the IBTA specification, but it is different. I'll take you through some of those differences as I go through. And one of the things that makes it different is the technology that we contributed to OFED. Okay? And then the last point, I am a marketing person. So everything I say, and I'll let you fill in the rest. So we entered the InfiniBand space in 2006 with the acquisition of Pascal and QLogic, or excuse me, Silverstorm. And those acquisitions gave us the HCA, the ability to design switches all the way up through director class switches. And the key point here is the TrueScale architecture, which is the name for our InfiniBand, was architected after it became very clear in the InfiniBand space that InfiniBand was not going to be a replacement for PCI bus or as part of the enterprise and so forth. So if you take a look at it, when InfiniBand was originally being spec'd, and if you go all the way back, who remembers NGIO and Future IO and so forth? Okay, but you got to go back a long way. But that was the basis for what InfiniBand was supposed to be. So if you architected at that point in time, you came up with a very different architecture than if you waited 4 or 5 years and became very clear that InfiniBand was not going to really take over the enterprise data space. It was going to be focused on HPC. And we had the benefit of that just because we were late. But we were architected at that point. Now, QLogic produces our own end-to-end solution. We have our own silicon for both the switch and the HCA. We do our own HCAs, we do our own switches. Those switches range in size from an edge switch as small as 18 ports, all the way up to director class switch with an 864 port profile. We also run OFED, and we have what we call our OFED Plus version, which is based on OFED with some surrounding things predominantly for management and ease of installation and maintenance and troubleshooting of a cluster. Now, the other last thing is we released our whole TrueScale product line. We announced it in 2008, the end of 2008. And we began shipping in volume in late 2009. And over the course of about the last year, we've actually done reasonably well. About 1 in 5 clusters today are based on TrueScale. So we're starting to gain some footprint. Still have a long way to go to catch up to Mellanox, but at least we've entered the marketplace and we're starting to have an impact. So let's get into the architecture a little bit. TrueScale does not use an offload engine on the HCA. So the HCA does not have an offload. And from our standpoint, it's hard to keep up with Moore's law and Intel. The processing power of today's Nehalem's, Westmere processors, dual socket, quad socket, it's hard to really keep up with that. And our contention is that gets in the way. Our approach is basically to leverage the processing power of the host processor, but also with an interface that's specifically designed for MPI. And that was the piece that we contributed to OFED. Next. With that piece and how it's designed and its focus being tuned for MPI, it has a minimal impact on CPU utilization. It also does very well with collectives. Some very interesting information a little bit later on. We also provide advanced fabric features for switch-based congestion detection. That's hard to say. Switch-based congestion detection as well as adaptive routing. The benefit of that, and I'm going to assume it's somewhat similar to what Mellanox does, is that every switch in the fabric is looking for congestion. When it detects it, it automatically adapts the routes. So there's no software involved, it's basically all hardware. Since it's switch-based, it scales with the size of the fabric. To also help with congestion, we also do something called source-based dispersive routing. Every single host, and you can turn this optionally on, has the ability to select paths, all the paths that are of equal length in the fabric, and spray messages across them. So the benefit of that is it's another means for reducing the potential for congestion, starting at the host level. Combine that with what's going on at the switch, and we feel like we have a pretty effective means for handling congestion in the fabric. We also support advanced topologies for fabrics such as torus and mesh. We also have sophisticated fabric management, including we've done integration with platform at their management console level. So the view there is platform through their products manages the cluster. We manage the fabric. We've combined the two together at the console level. We've also combined with LSF, where we can do scheduling based on quality of service. We've also done that with adaptive MOAB. Okay? And we work with NVIDIA's GPU Direct. In fact, we ended up with a number 3 on the top, or on the Green 500 list with NCSA. Some of you may be familiar with that. Next slide. So let's get into it. PSM stands for Performance Scaled Messaging, was added as part of OFED 1.3. It's an InfiniBand library and API specifically designed to maximize the performance of MPI. It's already integrated with all MPIs. So any MPI such as OpenMPI, Intel MPI, Platform MPI, all the various MPIs that are out there. It also works across all the collectives and so forth. Now the thing that makes PSM so special, it's a really good match to MPI and the semantics of MPI. And because of that, it's very efficient and it's optimized while still minimizing the impact on CPU performance. Next slide. So what it uses basically, PSM is a very lightweight. It's about 1/3 the size, or 1/13 the size of verbs. And it's designed specifically and only for, at this point in time, MPI. So at TrueScale, when you're doing things like SRP or SDP or IP over IB, we use verbs. And verbs is very well designed for that. PSM, though, is specifically designed for MPI. So it's a very lightweight module. It's connectionless. So we don't have to establish connections and maintain those connections and maintain all of that state information. And because of that, we don't run into the issues of a cache miss, where then things have to stop, go across the PCI Express bus, go to main memory, pull it back in, and so forth. Next slide. Oh, go back just one more. And because of that design, we achieved some relatively high message rates, especially with short messages that would be associated with MPI, but very specifically, MPI as you scale the cluster up. Because as you know, as you start to scale a cluster up, there's more communications going on between all of the nodes, processors, and cores. The message size tends to drop. Because of that, we actually do reasonably well. For non-coalesced messages, about 25 million. Relatively low latencies, 1.3. And with up to 1.5 milliseconds, or microseconds, excuse me, as well as our collective's performance with no special acceleration code, whether host or fabric-based, just native to PSM, we achieve, even at scale, very good latencies. Now, again, I'm a marketing person. So the question is, okay, I'm saying all this crazy. Let me, though, have somebody else who's actually implemented one of the first OFED 1.3 with PSM implementations, actually kind of go through their experience with it and the use of PSM as part of OFED. Want to do the...
Okay.
Now, before you start it, this is Lawrence Livermore National Labs. Matt Leiniger is the deputy director for Lawrence Livermore. And he did this presentation at Supercomputing. I'm only going to play the last 3 minutes of it. It is available on the QLogic website. So if you want to see the whole video, I'd encourage you to go out there. Okay?
Here's something.
So this one's very interesting. This is one of our codes. It's really one of our workhorse codes. It's one of our most complicated
No better?
physics codes. And the scalability of it is usually
Cannot do it better.
be very harsh, but this
Be in stereo.
on systems. And this is a historic graph of many systems, but what I want you to really look at is this bottom curve here in the blue. That's Sierra. So on the vertical here is grind time. The lower it is, the better it is. As you move to the right, it's scalability. So the flatter it is, the better it is. This is comparing Sierra here. You see in here, there's some older Linux clusters. This red line is actually a Cray XT system. These blue lines are some Blue Gene systems. Some of these up here are some older Linux clusters and older power systems. But to date, on this very intensive application, Sierra is the best scaling machine we've ever seen. We're still analyzing what all effects of or features of the QLogic network are really enabling this, but we certainly have several ideas. We're continuing our analysis right now, but the scalability of the IV fabric is certainly the best we've seen of any machine of this type out to about the 24,000 cores of Sierra. The latencies we're seeing on the fabric, certainly when it's not real congested, is on the order of 1 to 2 microseconds, which is very good across the 2,000 node machine. We're also seeing the message injection rate, how many messages you can push into the network at a given time. As you look at the small, kind of a 4-byte type message, is really, really high. We think that's part right now of what we're digging into in the analysis of what's really giving us the scalability, both the performance of the MPI collectives, which we're starting to look at, benefit from that dramatically. I don't have data on it yet, but we're also looking into advanced routing features, congestion control features, and toiling with them to see if we can get better performance out of the network as well. We've also been working very closely with QLogic in their PSM layer. That is, I think, a big part of why we're getting this good performance. Is now released in open source and will be available, or is available now, I think, in the Open Fabric stack. So those are some of the basically the highlights of what's been going on at Livermore and where we're at with these clusters. We're looking forward to using them. Most of them are either pushed into production now or on the verge of getting into production. So our users are very excited and starting to test their applications and scale out, doing even more tests than I mentioned here. So with that, I'll be happy to take any questions.
All right, do you want to switch to back?
Okay.
Next slide. Next slide. Wake up. All right, next slide. You went the wrong way. I've only got 4 minutes left, Peter. Let's get let's go to the next slide. Next one. All right, so what Matt was discussing is on this slide. If you do the next build, Peter, the bottom line is a cluster that they call Sierra. It's about 2,000 nodes, almost 24,000 cores. And they run a specific test that tests basically performance, and the lower is better. And essentially what this is what they call grind time per iteration. And perfect scaling would be a line that runs along the x-axis. And true scale with PSM basically was the best performing cluster. In fact, the red line that he referred to is a Cray system with its proprietary interconnect and approach. So this is InfiniBand basically going up against some systems that are proprietary interconnects and so forth. Again, some very good performance, actually about 2 times the performance of that Cray system. So they've gotten some very good results with PSM. Next slide. This is another test that they ran, or specifically it was the Xeon 5670 or Westmere. And comparisons, again, flatter and lower is better. And they got some really good performance numbers there. In fact, the scalability of the 2 lines in the center, which are both true scale-based InfiniBands with PSM, one being Sierra, which is a non-classified cluster, and the other being Muir, which is one of the classified clusters. They got some very good performance results with yet another application. Next slide. And just to summarize, because it was a little bit hard to hear, hit the next set of builds. Scalability looks good. Latency looks very good across a cluster of 2,000 nodes. Message rate injection was very good. Collectives have some interesting results I can share with you later on collectives if you would like. But just in general, all of these results were a function of, in a large part, PSM being designed for MPI, PSM being very lightweight, PSM basically being matched to how MPI really wants to perform and so forth, or really wants to communicate. All right, I think I'm on time. I could go, these are some of the advanced features, but I'm out of time. But this would be dispersive routing, quality of service. I have some interesting results on that. So if you want to, look me up after this, I'll be willing to spend as much time out in the hallway talking with you. Okay, thank you very much. And I want to thank Mellanox, 1, for giving me the opportunity, and 2, for being gracious about it. So thank you very much.